Hello students, today we are going to talk about a topic which is very important for your upcoming NEET examination and all for your board examinations also. And this is a very important part of the inorganic chemistry, and class 12 inorganic chemistry there is a very important chapter that is called coordination compounds. So today we are going to talk about that one part of the coordination compound, that is the bonding feature, and it's very important and it's known as our crystal field theory. Now some of you say it's a CFT, okay, but remember one thing, the beta basic idea about the bonding present in the coordination molecules is basically same. But what we actually here we do, kuch observations from the VSE pair theory we are not able to explain, lekin using this crystal field theory we are able to explain those. Say as simple as that. Now coming to the feature, remember one thing, that always the metal ligand interaction, we try to modulate this thing. Okay, we always try to modulate this metal ligand interaction. Now when we say metal ligand interaction, that means that ligand will donate the electrons to the metal, and thus since the metal is an electron deficient species, so it will closely attract the electron and it will stay at its. Now the thing is that this metal ligand interaction, what people usually does, they say that different theories or different cases, but the most important thing is that what we are going to assume in this crystal field theory is that the metal ligand interaction, is purely ionic, okay, means there will be an electrostatic interaction between the metal, your metal center, and the ligand, the approaching ligand. This will be a completely an ionic interaction. Number two, another important point is that here the ligand is considered as point charge. Point charge means when you have a metal, now around that metal you are basically a ligand, when it approach, it actually basically it's a point charge, so it will be a completely charge to charge interaction. That is the important thing. Okay, so if I go by then this logic, first we need to think about that when a ligand approaches to the metal, where it actually hits. Now the correct answer is that when the ligand approaches to the metal, it actually hits its atomic orbitals, and we know that this one contains the d electrons. This one contains d electrons, or if I take some of the f metals also, it will take f electrons. So these d electrons are basically, then it will be interact with the d orbital. Now let's see some of the d orbital. If I talk about any octahedral complex, let's say, suppose I am talking about an Ml6 complex. Okay, now in this Ml6 complex, the metal has what type of orbitals are there? There is dxy, dyz, dzx, dz square, dx square minus y square. Now the basic idea is exactly same. Here the dxy, dyz and dxz, they are basically in between the axis. Okay, if you see that, they are basically in between the axis. But if I talk about dz square and dx square minus y square, beta, they are basically along the axis. Okay, so if an ligand approaches via your axis, then what will happen? Then the metal will interact with the ligand, and the metals x square minus y square and dz square, both of them will interact. But if the ligand approaches in between the axes, then xy, yz and zx, these orbitals will interact. As simple as that. Now the point here, next point. Now coming to this fact, this interaction in the Ml6 cases. So let's say I'm telling something that, okay, chalo sir, say metal have the overall d orbitals, and in this case what is happening? In this case, let's say metal and all ligands are approaching. All ligands are approaching towards the metal. Now in this case, beta, one thing you should remember, that it is not necessary that only 6 ligands will approach. The many number of ligand approaches, like you can term this case in biology also, like when fertilization happens. to an egg, there are a lot of spermatozoa they attacks, right? But only one gets succeeded. Similarly, here also many ligands attacks the metal center, but only 6 get succeeded. Now, which 6? That's the important thing here. Thing is that now initially what happens, the metal was initial state, that is called the ground state, right? So this is basically a ground state, initially a stable state. Okay, and stable state, and this is your metal N plus. Now what happens, the ligand approaches. Now definitely when a ligand approaches towards the metal, the orbitals of the metal gets energized. Okay, now due to this energization, what happens, there is a shift of the energy of the d orbitals, shift of energy to a d orbitals. This is the energy direction, so shift of that. This is called your spherical. You can see here that all the ligands have already approached to the metal center. This is called spherical charges. This is called spherical charge distribution. Spherical charge distribution. Now in this case, once this spherical charge distribution happens, the metal realizes कि देखो बेटा ligand आ चुका है अभी. अब ligand को देखना होगा कि will interact with the metal. How it can do that? Now see one thing here, that the ligand, the safest way to approach the metal is that the ligand should approach at the via the your axis. Now if you see an octahedral complex, this is an octahedral complex. So let's say if beta, this is my x-axis, this is my y-axis, and this is my z-axis. So basically the ligands, if you see, they all are approaching towards the from the your axis, right? Now if I go back to the structure of the d orbital, now the ligands which are approaching along the axis, they will directly hit dz square and dx square minus y square, and they will indirectly hit yz, zx and xy. Now actually what that happens now, since this was a completely degenerate state of the d orbital, now this one gets splitted. Now into this splitting, what actually happens, the two orbitals which are basically directly interacting with the metal center, that is your dx square minus y square and dz square, they gets energized, and rest of the cases where you have yz, zx and xy, they actually get de-energized like this. So basically, it's okay. So basically this state is called EG set of orbitals, and this set is called beta T2G set of orbitals. Now in this EG set of orbital, what we have, dz square we have, and dx square minus y square we have, and T2G set what we have, T2G set we have dxy, dyz and dxz, right? So these things we have, these orbitals. Now beta, this gap is called delta O. This O stands for octahedral density, octahedral, and this center is called zero center. If you draw a center from the excited spherical charge distribution, this center is called barycenter. This center is called barycenter. Okay, and the one last thing is that here, this gap, this first gap is basically you called this, the value of this plus 0.6 delta O, and this gap from the 0 level to T2G gap, this gap is called minus 0.4 delta O. Now the thing is that this is called octahedral splitting in crystal field theory, octahedral splitting. Okay, so I am writing here the term octahedral splitting. Okay. Now the thing is that you can ask one thing, sir, that this delta O can vary, right? Now, if you see, remember correctly here, when the ligand approaches the metal, then this delta O, this orbital gets splitted. That means your more stronger the ligand will be interacting with the metal, higher will be the gap. Simple logic. Okay, I am telling you again, more stronger the interaction with the metal of the ligand, higher will be the gap and higher will be the splitting range. Now, so basically what we can say that this value of delta O depends on your nature of the ligand. Depends on the nature of the ligand. value of your delta O depends on the nature of the ligand, and due to this nature of the ligand, what actually happen, you basically have a range of different type of complex. और ये जो part है, that part can be completely explained by something called spectrochemical series. Something called spectrochemical series. Now, and you check my another video where I have already talked about the spectrochemical series. Okay, so I will not discuss that here. Now, the thing is that when we talk about this nature of the ligand depends on how much we talk about, then what is this energy of this state, right? Now, that energy, basically what happens, this energy, when after the splitting, what happens to the metal, that energy actually stabilizes the system, and that is called my crystal field stabilization energy. Crystal field stabilization energy, or it is called CFSE. In short, it's called crystal field stabilization energy. Acha. Now, how to calculate this thing? I will just use simple example. Suppose I have these two states. Let's say there is an case here. Let's say there are 3 electrons here and there is 1 electron here. Now, remember one thing, that this is your 0. Tale beta, this gap is your plus 0.6 delta O, and this gap is your minus 0.4 delta O. Correct? Tale, remember one thing here, the CFSE, the way we will calculate here, it is basically here your 3 into minus 0.4 delta O plus 1 into 0.6 delta O, right? So this will be is equal to minus 1.2 delta O plus 0.6 delta O. That means it will be minus 0.6 delta O. This is your crystal field stabilization energy, and if the value is the minus, that means the complex is stable. Now let's take an example here. Another thing, let's talk about something called your D6 system. D6 system. Now beta, in this D6 system, let's first draw the D6 system. 3, 4, 5, 6. Sorry, D6, right? Now what will happen? Now let's say there is a ligand that will strongly dissociate and another one that is weakly dissociate, right? So let's say if case of it is strongly dissociates, then it will create a huge gap between this T2G and EG scale. And if it is weakly dissociates, that is for a weak ligand, if I talk about, that is basically your, it will be small gap, means this delta O is higher, this delta O is lesser. Now let's see if I talk about this D6 system. चलो इलेक्ट्रॉन डाल देते हैं यहाँ पे 1, 2, 3, 4, 5 and beta 6. Now this state where you have a weak field ligand, okay, there is a system weak field ligand, and in this system you have a strong field ligand. Okay, means a weak field ligand actually weakly dissociates the gap, when a small gap, and for strong field ligand the gap is very high. चलो अगर हम इलेक्ट्रॉन यहाँ पे डाल देते हैं, देन क्या होता है देखते हैं. Now 6 will be arranged 1, 2, 3, 4, 5, 6. Beautiful. So 6 electrons will be arranged according to the Hund's rule. But in this case, the Hund's rule will not be followed by, because electrons are not that much enough energized so that it can go to the EG level. Okay. Achha. So 1, 2, 3, 4, 5, 6. Okay. So if I talk about the electronic crystal field electronic configuration of the system, then what I will write here, it will be your T2G 4, EG 2, and in this case here will be T2G 6, EG 0, right? Now let's say beta, if I calculate the CFSE of these two systems, what I will get? देखते हैं बेटा, चलो CFSE in this system what I will get? I will get here 1, 2, 3, 4. So 4 multiplied by minus 0.4 delta O plus यहाँ पे क्या देखेंगे बेटा 2 multiplied by 0.6 delta O, and there is one pair also. So what I will write here, one pairing energy. So this will be equal to minus 1.6 delta O plus 1.2 delta O plus P, and that will be is equal to how much? That will be equal to minus 0.4 delta O plus P. Right? So this is the crystal field energy for this kind of complex, weak field, and this is your high spin complex. This is your high spin complex. Now beta, for this case, for how much we will get? It will be getting directly, this contribution will be 0. So what I will write here, it will be minus 0.4 delta O into 6 beta plus 0 plus, there is 3 paired electrons, so 3p. Now in this case, what I will write, minus 1.2 delta O plus 3p. Now see, in both cases, if I see the value, in this case your pairing energy is higher. Okay, your pairing energy is higher. So if your pairing energy is higher, then what we can say that, acha chalo beta, if I take a difference here, chalo, then what I will get? I will get that if a case that for strong field ligand, the pairing energy is much higher, right? Pairing energy higher and delta O is much lesser. So remember one thing, if your pairing energy is higher, then the system will not attend the pair, because in this case, always remember, for this case, your pairing energy will be always higher than delta O, so that if the pairing energy is higher, the electron will not be tend to be paired. But in that case, your delta O can be minimum. But in this case, remember always, your pairing energy will be lower. Your pairing energy will be lower. So in this case, what happens? So that the electron can get paired. And this actually depends on what? This actually depends on your nature of the ligand. Okay, so fine, this was something all about your today in the crystal field theory and the CFSE calculation for this system, and what is the idea about the strong field ligand and the weak field ligand also. Fine. So I hope you liked the video. If you have any question from here, then feel free to write in the comment section. So till then, from my side, hello, bye everyone, take care.